Welcome everybody to the second Vlogmas video. Today I'll be doing a video about math, mostly because my life was really boring in the past 2 days and I didn't really do anything. So I wanted to do a topic in elementary number theory because it's an area I really enjoy and I think it's accessible to a lot of people. So I'm going to talk about the sums of two squares today, and I'll talk about two results that have to do with that. So the first one is, if we have a positive integer n, when can we write it as a sum of two integer squares? So when can we write n equals x squared plus y squared, where both x and y are integers? And now an extension of this, once we know if a specific integer can be written as a sum of two squares, what about on average? How many ways can we write a positive integer as a sum of squares? Now if we take the limit, so on average of all the integers, the number of ways you can write this is on average pi, which is kind of interesting, but it actually has to do with circles. So you can think about that while we go through the next stuff and see if you can figure out why. So first I'll do some definitions and some lemmas which we'll need for the first point. So the first definition is a representation n equals x squared plus y squared is called primitive if the greatest common divisor of x and y is 1. So some examples are 13, which is equal to 3 squared plus 2 squared, is primitive because the greatest number which divides both 3 and 2 is 1. While 20, which is equal to 2 squared plus 4 squared, is not primitive because both 4 and 2 are divisible by 2, which is greater than 1. Now we need this lemma. So the lemma says if n is divisible by a prime of the form 4m plus 3, where m is some integer, then n has no primitive representations. So let's prove this, and we'll do it by contradiction. So if you suppose n is divisible by a prime, which is of the form 4m plus 3. So suppose, by way of contradiction, that n is divisible by a prime of the form 4m plus 3, and that we can write n as a sum of squares, x squared plus y squared, where their greatest common divisor is 1. So we just said p divides n, so p divides x squared plus y squared. And from that we can infer that p can't divide x and p can't divide y. So why is this? Well, suppose p divides x. So since p divides x squared plus y squared, then we can write x squared plus y squared is equal to some integer k times p. And now if p divided x squared as well, we can write x is equal to some integer l times p. This is just by definition of divisibility. So now if we do all this math, we can conclude that p also divides y, which is a contradiction, since if p divided both x and y, the greatest common divisor of x and y would not be 1, it would be at least p. So this is why we can't have p dividing x or p dividing y. Okay, so since p divides x squared plus y squared, we know that x squared plus y squared is equal to 0 mod p. And also, since p does not divide y, and so does not divide y squared, then y squared is not equal to 0 mod p. And let me just remind you, so if we have the set of numbers from 0 to p minus 1 and p is a prime, this forms a field. So a field is where every non-zero element is a unit, so you can divide by it. And so since y squared is non-zero, we can divide by y squared. So we have, by our equation up top, 0 mod p is equal to x squared plus y squared mod p, but we can just divide this by y squared. So 0 mod p is equal to x squared plus y squared, all divided by y squared mod p. And now you can rewrite this nicely and conclude that x over y squared is equal to minus 1 mod p. But this implies that the Legendre symbol of minus 1 over p is 1, because minus 1 is equal to a square mod p. But if you actually compute the Legendre symbol with the formula, and since p is equal to 4n plus 3, you'll get that it's actually equal to -1, which is a contradiction. So we contradicted that n can be written as a sum of squares where their greatest common divisor is 1. And so we've proven this lemma, which we'll need in a little bit. And now we have a second result to prove. This result's actually called Fermat's little theorem, maybe familiar to some of you. So Fermat's little theorem says if p is a prime and a is any integer not divisible by p, then a to the power of p is equal to a mod p. So there are many different ways to prove this, but I'll just use the simple way, go by induction. Induction on a. So when a is equal to 0, this is just trivial. 0 to the p is equal to 0 mod p. And now let's move on with the induction. So suppose a to the p is equal to a mod p for some non-negative a. Now what happens with a plus 1? So a plus 1 to the power of p, we can rewrite it using the binomial expansion like so. And now we know 1 is equal to 1 mod p. And if you take where k goes from 1 to p minus 1, this binomial coefficient p choose k will always have p in it. So this whole thing is equal to 0 mod p, just disappears. And then by our inductive hypothesis, a to the p is equal to a mod p. So we get the total is equal to a plus 1 mod p. So now let's get to seeing when can a positive integer be written as a sum of squares. So it turns out that a positive integer n is the sum of two squares if and only if all prime factors of n of the form 4m plus 3 have even exponent in the prime factorization of n. Okay, so this is an if and only if statement, so we have to prove both directions. I'll first start with the forward direction. So I want to show that if n is the sum of two squares, then all prime factors of n of the form 4n plus 3 have even exponent in the prime factorization of n. Okay, so let's write out our prime decomposition of n and take one of the pi's that's of the form 4n plus 3. And we'll suppose by way of contradiction that the exponent of pi, which is we call ri, is odd, and we want to get a contradiction. So we wrote n is equal to x squared plus y squared. So let's write the greatest common divisor of x and y as d. So that means d divides both x and y. So we can write x equals to dx prime and y equals to dy prime for some x prime and y prime in z. So now if we compute this all, we see that n is equal to d squared times n prime. And since d was the greatest common divisor of x and y, then the greatest common divisor of x prime and y prime must be 1, otherwise, and get a greater GCD of x and y than is d. So we have n is equal to d squared times n prime, and we have that ri is odd. So since pi divides n, even if pi did divide d squared, there will still be a leftover factor of pi. So that means pi must divide n prime. But we have pi is equal to 4m plus 3. And also n prime is equal to x prime squared plus y prime squared. But the GCD of x prime and y prime is 1. And by our lemma, we say it has to be greater than 1. So we have a contradiction. So let me remind you what we just proved. So if we wrote out the prime decomposition of n as p1 to the r1 times pk to the rk, and if we suppose one of the pi's is of the form 4n plus 3 and it has an odd exponent, we got a contradiction. So it means if pi is of the form 4n plus 3, it has to have an even exponent. Okay, so now we have to prove the backwards direction. So this is saying This is saying if all prime factors of n of the form 4n plus 3 have even exponent in the prime factorization of n, then n must be a sum of two squares. So first let's split n into two factors. So we have n is equal to n1 squared times n2, where n2 has no prime factors of the form 4n plus 3. This is forcing any prime factor of the form 4n plus 3 to have an even exponent. So all we have to worry about is what's happening in n2, because if n2 is the sum of two squares, so n2 is equal to a squared plus b squared, then we can write n as n1a squared plus n1b squared. So no matter what n1 is, we don't have to worry about it. So it's enough to show that n2 is the sum of two squares. And also note that if two numbers are the sum of two squares, then so is their product. So you can verify this formula I wrote. Okay, so let's write our n2 into a prime factorization with these primes p1 to pk, and none of them are of the form 4n plus 3. So that leaves us with each of these pi's is of the form 4n plus 1 or 2. And 2 is a sum of squares clearly because 2 is equal to 1 squared plus 1 squared. It's enough to show if a prime p is of the form 4n plus 1, then p is equal to a sum of two squares. So then, because all of these will be a sum of two squares, their product will also be. So this is a theorem of Fermat, and we'll use a proof of Euler to prove it. I use Fermat's little theorem, which we proved not long ago. So I'll just remind you what it says. So if a is an integer not divisible by a prime p, then a to the p is equal to a mod p. So since a is not divisible by p, a is not equal to 0 mod p. So again, we can divide into field z mod p. So this is equivalent to saying a to the p minus 1 is equal to 1 mod p. So in our case, p is equal to 4m plus 1. So p minus 1 is equal to 4m. So all the numbers less than p can't be divisible by p. So by Fermat's little theorem, we have 1 and then 2 to the 4m, 3 to the 4m, and so on, up to 4m to the 4m are equal to 1 mod p. So now let's take the differences of them. So these differences are equal to 0 mod p. So they're divisible by p, each of these differences. And now, notice, so each of these differences is of the form a to the 4m minus b to the 4m. And you can rewrite this as a to the 2m plus b to the 2m times a to the 2m plus minus b to the 2m. So since p divides this difference, it has to divide either a to the 2m plus b to the 2m or a to the 2m minus b to the 2m. So Euler proved that if you have a number of the form a to the 2m plus b to the 2m, then every factor is a sum of two squares. So the only way it's possible for p to not be a sum of two squares is if p divides each of these. So the one that's like a to the 2m minus b to the 2m, so they look like this. So again, we'll suppose that this is true and then see that it can't be. So if this is true, so then p must divide each of the differences of these two. So you can write them like this. So 3 to the 2m minus 1, 4 to the 2m minus 2 to the 2m, and so on. And then you can keep going, and p will keep dividing the differences. And we know that the kth difference of the sequence 1 to the k, 2 to the k, 3 to the k, all of these are equal to k factorial. So if we do what we did above and get to the 2m's differences, then p must divide 2m factorial. But that's not possible, so we get a contradiction, and we have proven our fact. Okay, so now we get to the part 2 of this. We know when you can write a number as the sum of two squares, but how many ways can you do it? On average, how many ways can you do it? And we'll see why this is equal to pi. On average, in how many different ways can we write a positive integer as the sum of two integers squares? So let me write a function for that. So I'll let an be the number of ways to write n as the sum of two squares, where n is a positive integer. So what do I mean by an? Here are some examples. So a of 2 is 1, since all you can do is say 2 is equal to 1 plus 1. A of 3 is 0. So if you remember from the last theorem we proved, 3 is a prime of the form 4m plus 3. And so the prime decomposition of 3 is just 3, since it's a prime. So by that theorem, it says you can't write 3 as a sum of two squares, so a of 3 is 0. And a of 5 is 2, since you have 5 is equal to 1 squared plus 2 squared, and 5 is equal to 2 squared plus 1 squared. And you might be saying, that's the same thing. Well, here we'll distinguish a, b, and ba, where a and b are different. So a circle with radius r, centered at the origin, the equation's x squared plus y squared is equal to r squared. So if we look at the equation we're considering, so x squared plus y squared is equal to n, this is a circle of radius square root of n, centered at the origin. So really, if a pair of integers satisfies this equation, a pair of integers xy, this means xy is on this circle of radius square root of n. And this is why we distinguish xy and yx when x and y are different. So like the point 1, 2 on a circle is different than the point 2, 1. So now we can think of an in a more geometric way. So what an is doing, it's counting the number of lattice points on the circle of radius square root of n. And lattice points just means a pair where both elements in the pair are an integer. And now let's sum up all the pairs xy which satisfy this equation just for a specific n, but we want to say on average. So an counts how many pairs xy satisfy this equation. And what does that mean? So when you take the average, right, you sum up all you have and then you divide by the number of things that you have. So first let's start by summing. I just see that there's a typo on here, so I want this to be sum of ai, not an. So if we sum up all the ai's, where I goes from 1 to n, and let's call this equation big N of square root of little n. What big N is counting, it's counting the number of lattice points on or inside a circle of radius square root of n, right? Because the biggest circle here has radius square root of n, and then ai, for when I is less than n, it's counting the points on some circle with radius less than square root of n. So this is what this equation does. And this is actually a well-known problem called the Gauss circle problem. So Gauss proved if you have a circle of radius r, then n of r is pi of r squared plus some error term e of r, where the error term is bounded by these values, so minus a constant times r and plus some constant times r. The bound was made smaller eventually, but we don't need that smaller bound for this problem. This bound is enough. So when we're looking at the average, like I said, we want to divide the big N by the little n. And so we have this nice equation for our big N, and we can rewrite this like that. So now if you just want to know on average what happens, we'll take the limit as n goes to infinity. Then the number of ways to write a positive integer as the sum of two squares is the limit of n approaching infinity of big N square root of little n over n. And we'll see this limit is really equal to pi, which is interesting. So we have this bound for e, and what this means is that e of square root of n is in between these two terms. Okay, so now let's add pi of n to all of these, to this inequality. And again, let's divide by n. Since n is a positive number, it's okay. So now we get this new equality. And we'll use our friend the squeeze theorem. So on the left side, we take the limit as n goes to infinity and we get pi. And again, on the right side, we take the limit as n goes to infinity and also get pi. So by the squeeze theorem, we get that this limit is pi. And what that's saying is the average number of ways you can express an integer as a sum of two squares is pi, which is, I think, pretty neat. Okay, so thank you so much for listening to this. I hope you found it cool like I did. And I'll see you in the next Vlogmas, which will be a vlog this time. Bye bye.